Hi, welcome. Are you here for EGME 441?
Yeah.
Welcome. Take a seat. Wait, what? You are the first one, yeah. Still a little bit early. What's your name?
Steven.
Steven, nice to meet you. So nice to be in person again.
Yeah. I have you last semester.
Oh, okay.
Yeah.
Oh, sorry, you were in Hong Kong last semester? Or somebody else?
In China.
Oh, China, okay.
Yeah, it's not good for me to 8 and 9.
Oh, yeah, yeah.
And I didn't drink wine that semester.
Yeah, it's always really hard when it's like, because probably like your family and stuff were like asleep at the time and like your whole sleep schedule was inverted too.
Sometimes I fall asleep and I had to watch the recording video again, but sometimes it's too late to watch it.
It's hard when it's like all virtual like that. But
Yeah.
but happy you're here. Glad to have you.
Also, we also have the also online for
Yes. Yeah.
optional.
Yeah, so it'll be both because some people are still a little bit uncomfortable coming to the class, and so I want to do kind of both for them. Yeah. Mhm. Hey guys, welcome.
There's a little poster section. I
got two from my sister and you know.
How are you doing today, Dr. Tran?
I'm good. How are you guys? Good to be back. Actually, I'll be right back. I need to grab my notes. I just realized because usually I have my notes on my computer screen right here, but if I'm sharing screen for the virtual people, then I can't read my notes and have you guys follow along at the same time. So I need to go back to my office and get my notes. Yeah. And so I kind of went back and forth a lot over the last few days, but I know because a lot of students are saying they still don't feel comfortable, and so I want to be here in person just because we set this to be in person. But if you want to take it virtually, then you can do that as well. Yeah, you can do both. The only thing is the exams will be here, and so for the exam dates, you guys have to be here. But for a regular lecture, you can be at home or you can be here. Okay, I'll be right back. I'll be back in like 5 minutes. Hey, welcome. All right, welcome. All right, it's 4 o'clock. So let's go ahead and get started today. All right, good afternoon, everyone. Welcome to everyone here in the classroom. So thank you guys for being here. I know it was kind of a weird, awkward first week, but happy to be here. It's weird. It's like it's my first time in front of a classroom in a long time. I have like jitters again. It's like kind of strange. But thank you guys for being here, and thank you everyone for being here virtually as well. Can everyone on Zoom hear me? Okay.
Yeah, I can hear you.
Great, great. So I went back and forth a lot on how I'm going to do this, because originally what I had planned was to kind of have a setup like this and just write on the whiteboard kind of normally. But as you guys can kind of see from the camera here, like it doesn't really catch the whiteboard all that well. So I figured probably the best thing to do would just be to use my normal setup with Zoom, but to also just kind of be here physically in the classroom with you guys. So I think this was, we'll try this for a while and see if this works, and then we'll adjust as the semester goes. But yeah, thank you guys for being here. So especially for this class too, because it's a brand new class, and so I really appreciate you guys being here and being patient with me as we kind of figure this thing out and come back to campus. But all right, so the plan for today, now that we kind of got all the introduction stuff out of the way last week, we're kind of entering a period in this class we're going to be focusing on review. Okay, because like what we talked about last week was that biomechanics is not something that's really new or really challenging. A lot of you guys already have all the knowledge already. It's more just applying it to biological systems. I think that's kind of the tricky part. And so today, the subject is going to be just math review. It's not particularly difficult math too. I'm having a hard time breathing because of the mask. It's mostly just going to be vector and matrix algebra. So probably a lot of you guys know this already, but I thought we'd just do a quick review session just to make sure that we're all caught up, we're all on the same page. Okay. But I guess before that, let me start with kind of a funny story that happened over the weekend, just to kind of help me settle my nerves here. So I went to a wedding yesterday. It was kind of the first wedding I've been to since COVID began. But the funny thing was is that the people getting married, their family belongs to kind of a I'd say kind of a traditional religious kind of family. And so my fiance and I, we live together, but we're not married yet. But I think to them, if if two people live together, to them, that's kind of as good as being married. And so when they invited us and when we got to the wedding, they said, Mr. and Mrs. Justin Tran, even though we're not married yet. And so it was kind of funny, we got there, we got our name tags. I was like, we did it, honey, we got married. All it took was just to going to your friend's wedding and, and so it was kind of a funny joke that, we did that because we haven't planned the wedding at all yet because of COVID, but it was the first time that we'd been called like an official couple. So it was kind of a anticlimactic, but kind of a big moment for us at the same time. Okay, so let's go ahead and get started. Right. And so the subject for today's lecture is going to be just a review of vector algebra. Okay. You guys have no idea how nice it was to hear actual laughter after I tell a funny story like that. It's been a year of just telling jokes to my computer screen, and the only laughter I could hear is from my fiance laughing at me because I'm telling all these jokes and getting no reaction, and she's like, "What the hell are you saying?" So it feels so good to hear laughter again. So thank you guys for humoring me. Okay, and so let's get into vector algebra. So like we talked about last time, that the main challenge that we're going to face here with biomechanics is in kind of the complexity of the human body in terms of its geometry and its material properties, right? Of the lecture notes, I can make a PDF. Yeah. Okay. Because if you take away that, then it's really just mechanics, which we all kind of know already. And so before we kind of tackle those challenges of kind of complex geometry, it's good to kind of have a firm grasp of all what I like to call the engineering fundamentals. And so today we're going to do the mathematical fundamentals, and then for the next few lectures we're going to do kind of the mechanics fundamentals, so things like statics, things like strength of materials. Okay. Okay. And so, hopefully a lot of this is just, purely review. It's not even anything complicated like the differential equations or anything like that. It's really just vectors and matrices. Okay, so let's start with vectors. Okay. And so whenever I think of vectors, I don't know if you guys have seen the movie Despicable Me, but I always think of the supervillain in the first one where, he's like this really dorky dude in an orange suit, and he says, he says he does evil with direction and magnitude, and he kind of does this really weird kind of pelvic thrusting thing. And so that's how I always remember vectors. So vectors are always, they're characterized by two basic components, right? Okay. And so just like the villain, we have direction. Okay. Or in other words, another way to talk about direction is to talk about where the vector is pointing. Okay. And the other thing that characterizes vector is its magnitude. Okay. or in other words, how strong or how long it's pointing. Okay. Okay. And so visually, you guys probably noticed already that vectors are always denoted by an arrow or a directed line segment. Okay. And so we have kind of a starting point, and we have an arrow that looks like that. Okay. And we always denote it with some kind of symbol with a arrow over it. Okay. Right. And so you can see from this image here of kind of the two quantities, right? And so one of which is the direction, right? And so you can see if you kind of imagine that there's a clock on there, that arrow is kind of pointed towards 2 o'clock, I guess. Yeah, maybe about 2 o'clock. Okay. And so the direction, a lot of times the way that we characterize it is in terms of the angle that it makes. Okay. Because a lot of times that angle will tell you, how much the vector has rotated and where it's pointing. Okay. Whereas the magnitude is just simply how long this arrow is. Okay. Okay. And so, those two things are going to characterize our vector. Then a lot of quantities that we're going to talk about in biomechanics can be characterized as a vector. So the main one that we're going to be looking at a lot is force, right? And so we like to think about a lot of, what are the kinds of forces that the human body endures? What are the kinds of forces that our muscles can exert? What are the kinds of forces that are put on our bones or our joints? Okay. So that's going to be the main one. But then there's other things like momentum, things like, velocities. Vectors are really useful quantities when you're talking about any kind of applied mechanics. Okay, so any questions on this so far? Okay. All right, and so that's kind of the two main components of vectors. But a lot of times we like to express vectors in other ways. Okay. Because the definition that I gave you and the image that I gave you on the previous page, that's usually most useful for polar coordinates, right? And so when you have polar coordinates or cylindrical coordinates, a lot of times you express vectors in terms of the radius or the r and also its angle. But probably a lot of you guys agree with me too that polar coordinates are not usually the easiest ones to work with. And so usually we like to work in Cartesian coordinates, okay? And so the way that we express vectors with Cartesian coordinates is a little bit different, okay? And so the first way that I want to talk to you or tell you about that you guys probably already know is the component form for vectors. Okay. Right, and the way that we express vectors in this way is that we take an arbitrary vector and then we break it up into its so-called components in the principal directions. Okay. And usually the principal directions that we talk about, if we're talking about just a Cartesian space, those are things like the X and Y directions, or Z also if you're in 3D. Okay. And so let's take our image from the previous slide. Okay. And so let's say that we have just an arbitrary vector here. Okay. And so here's our vector v with the arrow on top. Okay. The way that we can break this down in terms of components is if we have our usual XY coordinate system like this, okay? Right, so where X just goes horizontally from left to right, and then Y goes vertically from up and down, okay? Okay. You kind of make this like kind of right triangle associated with it, okay? Where this length right here, this would be Vx, and this length right here would be Vy, okay? Therefore, we can express our vector in terms of these components Vx and Vy. And so what we say is that V with an arrow on top is equal to Vx, comma, Vy. Okay. And so if you're, if you're talking about just general Cartesian coordinates, this is probably how everyone kind of learned how to do that. Okay. A spin-off of this one, which is one that's used actually a lot in in applied math, is to put this in terms of unit vectors. Okay. And so the unit vector form is kind of a spin-off of this one. And so I don't want to make a whole new category, but probably another way that you've seen to express vectors is like this, right? And so instead of parentheses Vx comma Vy, another way that we've seen this expressed is a Vx multiplied by unit vector. Okay, the unit vector is usually I hat plus Vy times j hat. Okay, where I hat and j hat, these are unit vectors in the x direction and the y direction. Okay. And so, literally it would just look like this. Okay. And so the key word here is unit vector. And so a unit vector, all that means is that its magnitude is 1, or it's a vector with length of 1. Okay. And so, you'll probably see me use this version more often with the unit vectors, just because that's kind of traditionally how I was taught, at least in college. But in high school, I used the one more with the parentheses there on the right. Okay. All right. Any questions on this so far? Okay. All right. And so when our vectors are expressed in this form, we want to we want to compute things like its magnitude, its direction. Okay. And so when you have your vector in component form, you can compute the magnitude using Pythagorean's theorem. And so let's say that we have a 2D vector, and so the magnitude of the vector is going to be the x component squared plus the y component squared. Okay. And we give that the way that we denote that usually is with 2 vertical lines. And so whenever you see those 2 vertical lines on some kind of vector quantity, that means we're going to compute the magnitude. Okay. And then if you're in 3D, you just also add the z component too. So you have vx squared plus vy squared plus vz squared, all square root. Okay. And so the second one here is if you're in 3D, and this top one here is if you're in 2D. Okay. Okay. And then similarly, the direction. Okay. There's lots of different ways that you can find direction, and it actually gets a lot more complicated in 3D. But like we said before, that direction a lot of times you denote it with some kind of angle. Okay. And so if we take our our triangle here from the previous page, okay, and we want to solve for this angle right here, we can do that using trigonometry as well as the sides of the triangle. Okay. And so if we basically make use of the relationship that tangent of that angle theta is equal to the ratio of the opposite edge divided by the adjacent edge, okay, then what we can say is that tan theta is equal to Vy over Vx, okay? And so theta is going to be equal to tan inverse of Vy over Vx. Okay. And so this is one expression of the direction of the vector if we're in 2D using Cartesian coordinates. Okay. Okay. And so that's the component. That's the component form of a vector. So that's probably the one you guys are most familiar with. But another one that's used pretty commonly is called the unit vector notation. And so this notation here is I like to call it, it's like a little bit more true to what a vector represents. And so it kind of explicitly gives you one term that expresses the magnitude of the vector and another term that expresses the direction of the vector. Okay. And so the way that we express that is we say that our vector v is equal to magnitude times some kind of other vector here called a basically called our unit vector. Okay. And so this first quantity is the magnitude. And this quantity right here is our a unit vector. Okay. And this unit vector here will show us the direction. Okay. And so it's just another way to express a vector. And so here with this form, this is nice because you don't have to do any math to get the magnitude. You know, the magnitude you can just read off directly from the expression. And then, you know, the unit vector, it tells you the direction, but it does it in terms of, you know, of another vector. But the other vector has a magnitude of 1. Okay. And so I'll kind of show you how to compute these two things, you know, from, you know, basically to convert in between these two forms on the next page. But before I do that, are there any questions on this? Okay. All right. And so the magnitude, you know, we just covered, but let's talk about that unit vector that points in that direction. Okay. Okay. Remember, all a unit vector is just a vector with the magnitude of 1. Okay. And so in that sense, you know, it's just another way to express the direction, because, you know, that unit vector will point in a certain direction, but its magnitude will just be 1. And so the way that you find a unit vector, okay, and the way that I usually denote unit vectors is that I use this little hat notation here, okay. And so whenever you see me write a vector quantity with like a little triangle hat, that you can kind of already assume that the magnitude of that vector is going to be 1, okay. And so the way that you compute this unit vector here is you take the components. Okay. And so let's say that we have a 2D vector here. So we have Vx and Vy. Okay. And then what you're going to do is you're going to divide each of the components by the magnitude of the vector. And so by dividing each of the components by the magnitude of the vector, you're going to get a vector with a magnitude of 1. It kind of feels like circular talking, but, you know, it's kind of just how they're defined, right? And so visually it looks like this. And so if we take our vector from before, okay, so we have a vector v that points like that, okay? And let's say that this vector v has a magnitude of v with the 2 verticals, okay? The unit vector, you know, let's say that this vector here is longer than, has magnitude greater than 1. Okay? And so in that case, the v hat would just be a unit vector that points in the same direction as the original v, but it has a much smaller magnitude because it's you know, it's just a unit vector. Okay? And so these two things will overlap. It's just, you know, one will just be longer than the other one. Okay. Okay, so any questions on this so far? Okay. All right, so that's the basic definition of vectors, and so, you know, nothing too crazy there. And so now let's talk about what you can do with vectors. Okay, so let's talk about vector operations. Okay. All right, so there's a lot of things you can do with vectors. In fact, I have 6 of them, and so we have a lot to cover here. Okay, and so first, let's talk about kind of the simplest one, which is equality. Right, and so how do we determine if 2 vectors are equal? Okay. And so the way that we find this out is, two vectors are equal only if their direction and magnitudes are the same. Okay. Or another way to say this is that if you're using component forms for the vectors, then all of the components must be the same. Okay. And so, usually we'll probably use the second definition for this, right? So we're just going to check the components. And so if we have two vectors here, so let's say that we have u and then we have v. Okay. And so in order for these two vectors to be equal, let's say that u here is given by ux and uy, and then v here is given by vx and vy. Okay. In order for these vectors to be equal, both ux and vx have to be the same. Okay. And uy and vy have to be the same as well. So everything has a match. And so you can't just match one and say that they're equal, but everything has to match in order for vectors to be equal. Okay. All right. And so that's a vector equality. So fairly straightforward. Okay. And so now let's talk about what happens when you multiply by a scalar. Okay. And so a scalar is, you can kind of think of it as kind of one dimension down from a vector. A scalar is simply just a number. Okay. And so when you multiply a vector by a scalar, all you have to do is just either multiply the magnitude by that scalar, or you're going to multiply all of the components by that scalar. Okay. Okay. And so if you have a scalar quantity, so let's say that s is some number, so s can be like 6 or 7 or whatever your favorite number is. Okay. And you're going to multiply it by a vector v. Okay. And so the way to do this operation is you can either take the magnitude of v, okay, and then multiply by s. And so that's one way to do it. Okay. And then what this gives you right here is this is the new magnitude. This is the new magnitude of that vector. Okay. Right. Or another way to do this is just simply multiply this s by all of the components. Right? And so we have s times vx and then s times vy. Okay. Okay. And so the net effect of whenever you multiply a vector by a scalar is that you end up with either a bigger magnitude or a smaller one. Okay. And so it all depends what s is. And so if s is some number less than 1, and so let's say that's 0.5, your new magnitude is going to be half of what it was from before. Okay. And so whenever you see a vector multiplied by a scalar, most of the times you're doing that to modify the magnitude of for some reason. Okay. Any questions on this? Okay. All right. And so that's vector multiplication by a scalar. So let's talk about vector addition. Okay. And so you can add vectors together, or you can subtract them. That's fine too. Okay. And so when you add vectors together, the result is a new vector. Okay. Right? And so this new vector most of the times is going to be completely different from the vectors that you added together. Okay. And the way that you obtain this vector, this new vector, is just simply add all the components together. Okay. And so that's kind of the easiest way to do it. Okay. And so if we have a vector addition here where we have a vector A, okay, and this vector A is given by AX and AY. Okay. And then we have a vector B whose components are BX and BY. Okay. And so if we want to compute a new vector C, which is going to be the sum of A plus B. Okay. And so C, if we write it out in component form, we'll have AX plus BX. Okay, that'll be the X component of that vector. And then the Y component will be AY plus BY. Okay. So pretty straightforward. You're just adding the components. And you can come up with a visual representation of vector addition as well. Okay. And so let's say that if the vector A looked like this. Okay. And then let's say the vector B looked like this. Okay. When you add vectors together, visually what you can do is you can do what I like to call like tail to head. Okay. And so you take the tail of one vector and you put it on top of the other one. Okay. Okay. And so if we add B to A like this, we put the tail of B on the head of A. Okay. And if you take, the origin of the original vectors and you point it to where the endpoint is, like this. Okay. Right. That will exactly represent what C looks like. Okay. And so this is kind of another way to express this. Right? And so later on, when we're talking about things like, describing motion or describing, it's called gait analysis, which is, how a person walks. We'll be adding a lot of vectors together because, we'll have a vector going from your hip down to your knee, and then from your knee down to your ankles. Okay. And we'll use those vectors to kind of track the motion of your legs. Okay. And then, you can draw a resultant vector that goes from your hip to your feet. And then we're going to use these operations just like this. Okay. All right. So any questions on this? Okay. I know it's fairly simple so far, but with the fall semester, even I still forget these sometimes, and so I think it's useful just to go over, just to kind of make sure we're all kind of on the same page on this. So, okay. All right, so that's vector addition. Okay, so now we're going to get into a little bit the more interesting ones, and I think these are the ones that that I usually forget some of the properties for. Okay. Right, and so number 4 will be the scalar product. Oops. Okay. Or in other words, it's more common name that I think people usually learn is called the dot product. Okay. And so let me tell you kind of the end result of the dot product. So whenever you take a dot product between two vectors, you're taking two quantities that are vector quantities. And by the time you do the dot product, you end up with a scalar in the end. Okay. And so that's why it's called the scalar product. And so, that's kind of the result. Right? And so I think, most people learn dot products within the context of vectors, okay? But you can actually use the dot product on matrices as well. Okay. And so kind of the the characterizing characteristic for this is that you take two quantities that are of a certain dimension, okay? And then by the end result, you end up with something that's one dimension less, okay? And so a vector, you kind of almost think of it as kind of like a two-dimensional space because it has two components, okay? And then when you go down one dimension, then you end up with a scalar, okay? But you can also do a dot product between matrices as well, right? And so the operation for that is a little bit more complex. But if you take the dot product between two matrices, you end up with a vector, right? And so it kind of goes along that triage where you go, two vectors dot product, you end up with a scalar. Two matrices, you take a dot product, you end up with a vector. Okay. And so I like to think of the dot product as kind of an operation that kind of takes it down a notch. It takes it down one notch of complexity. Okay. All right. And so how do you actually perform this? And so if we have our two vectors, A and B, okay, and the dot product is, you literally just put a dot in between them. Okay. The way that you compute this is you take the components of the matching components, and then you just simply multiply them by each other. And then you add them to kind of the similar thing for the other components, okay? And so if we're taking the dot product between A and B, we're going to multiply both the x components for A and B, so AX times BX. And then we're going to multiply it by then we're going to add that to the product of the two y components of the two vectors, okay? And then if you have if you're in 3D space and you're at a z component, you can also do this as well. Okay. All right. And so that's kind of how you mechanically compute a dot product. Okay. But probably another application that you've seen for this is that, after you compute the dot product, you can set it equal to this quantity right here, okay, where you have the magnitude of A multiplied by the magnitude of B. And you multiply by the cosine of this angle theta, okay? Right. Where this angle right here, this is the angle that exists in between those two vectors. Okay? Okay. And so you have two vectors A and B. Okay. Theta is going to be that angle, right? And if you ever wanted to find the angle in between those two vectors, the dot product is one way to go, okay? Because this operation on the left-hand side is pretty easy to compute. It's just a bunch of multiplication and addition, okay? On the right-hand side of this equal sign, you have your magnitudes, magnitude of A, magnitude of B. Those are, you can compute those from the components pretty easily, okay? And then eventually what you can do is you can solve for the angle in between them, okay? And so this is kind of one of the primary, uses of the dot product is to find that angle using this relationship here, okay? All right. And so that's the dot product, okay? One other thing that we'll use the dot product for in this class is to find what I like to call a projection. Okay. And so projection, all that means is that, visually the way I like to think of it is if you have two vectors like this, A and B, okay, and you want to find out, if we shined a light coming from one end and go to the other one, what's the shadow that one vector will cast on the other one, okay? Or I should say, how long is the shadow cast from one vector to another? Okay. And so let me take these two vectors here, A and B up here, okay? And so when I say, I want to take a projection of A onto B, essentially what we're doing is we're doing something like this, okay? is we're kind of shining like a light bulb up here. And so you can imagine that there's kind of like a sun, okay? And then we're projecting this A onto B right here, okay? And we project it in such a way that this angle that I'm going to draw right here is 90 degrees. Okay. And so this angle right here is 90. Okay. Right. And so this line that I drew here, it intersects B at this point right here, okay? And so if I drew another vector that has kind of the same origin as the two, up until the point where they intersect, right? A lot of times we want to find out how long is this vector where they kind of intersect each other. Okay. Okay. And the way that you find the length of this vector is through the dot product. Okay. Okay. In other words, what we can say is that we're finding out, if two vectors are almost parallel to each other, how much of A goes in kind of the same direction as B, okay? Right. So personally, I've always found that whenever math classes try to explain projection, they always do, not to cause any drama, but I've always found that they do a terrible job. And so, it took me years and years of, of really advanced math to really understand what projection is. And so, hopefully this is a little bit more useful than what you guys have learned in previous math class, or maybe it's the same, I don't know. But that's kind of how I like to think of projection. And so when you see a dot product in between two vectors, another way that you can think of it is, how is it being projected from one onto the other? All right. So any questions on the dot product, scalar product? Yeah, question.
So what P dot A is just like how far past P, like how far past A, B extends.
Yep. Mm-hmm. Yep, and it's actually the same quantity. So if you do A dot B, B dot A is the same. You get the same thing, but that's another way to interpret it. And so if we do kind of the same thing, where we kind of make a line like this from B, right? Then the length of that vector will also be A dot B, and so it's actually the same thing. So you can interpret it kind of both ways. Yeah, yeah, great question. Mm-hmm. Yep.
So A dot B is like the projection of shadow. It's a scalar quantity, but like technically how we interpret it.
Yep. Yep. Yeah. So the direction would be the same in the same direction as B, but then the magnitude of that vector would be the scalar product in between the two. Mm-hmm. Yeah. Great questions. Okay, so that's a scalar product, and so now let's go over vector product. Or probably the other name that's most commonly used for is cross product. And so unlike the dot product here, the result of a cross product here is another vector. Okay. And so the definition I have is it multiplies two vectors in a way in such a way that it returns a third vector right? And this resulting third vector is going to be perpendicular to both of the two input vectors. Okay? Okay. All right, and so if we do A cross B, okay, the result of this is going to be a third vector C, okay? And this third vector C will be perpendicular to both A and B, okay? And so if we draw A and B as we did before, okay, so let's say this is A and B, okay? And so the direction of C in this case is going to be, perpendicular to both of these. And kind of the easiest way to think about this is that if your two vectors are kind of constrained within a certain plane, and so for you guys, it's constrained within the plane of your computer screen, or the projected board here, okay? Then a direction that's perpendicular to both of those would be either coming out of the screen or going into the screen. Okay? Okay. Right. And then, determining whether it goes out or comes in, the easiest way to determine this is the right-hand rule. Okay. Right. And so the way right-hand rule works, and I'll try to do this so people on Zoom can see, is that you take your index finger and you point it in the direction of the first vector in the cross product. And so in this case, the first vector is A, okay? And so you're going to take your index finger, point it in the same direction as A, okay? Then you're going to take your other three fingers, and so your other three fingers are this one. I think traditionally the way I learned it is middle finger, but I don't want to flick everyone off. And so you take your other three fingers and you point it in the direction of B, okay? While your index finger is still pointing in the direction of A, okay? And so in this particular case, I'm pointing in A, and then I have to twist my hand around to point my three fingers in B, okay? And then the direction of your thumb is going to be the direction of the last vector C, okay? And so in this particular case, I point my index finger in A, and then I rotate around to point my three fingers in B, and I see that my C vector here is going into the page. Okay. Okay. And so that's what it is for this particular example, is that it goes into the page. But of course, it depends on how you set this up. Okay. All right. And so to actually compute the cross product, usually the easiest way that I find is to use this kind of pseudo matrix inverse. Okay. Okay. And so let's form this kind of 3x3 matrix here. Okay. And on the first row of this matrix, we're going to have our three unit vectors in the XYZ direction. So that's I hat, J hat, K hat. Okay. Okay. Then you're going to write the XYZ components of the first vector, A. Okay. Oops. Okay. Then on the third row, you're going to write the components of the second vector, B. Okay. And then what you're going to do from here is you're just going to simply take the determinant of this matrix. Okay. And so if we take the determinant, we're going to cover up the first row and the first column. Okay. And then we're going to do kind of our 2x2 determinant. And so the first component here will be AX BY minus AY BX. Okay. Oh, I'm sorry. I kind of fucked it up already. Okay. Okay, so that's, I should just copy what I wrote down. So it'll be AY, BZ, okay, minus AZ, BY, okay. And all this multiplied by I hat, okay. Then we're going to subtract, and so if we cover up the middle column here, we're going to have AX, BZ, minus AZ, BX, okay. And this is multiplied by J hat, plus We cover up the third column. So this one's going to be AX BY minus AY BX A hat. Okay. All right. The formula looks a little bit intense, but if you just remember, just take the determinant of this 3 by 3 matrix, then you're golden. Okay. Okay. Any questions on this, on cross products? Yeah. Yes, yeah. So when you take the determinant of a 3 by 3, you kind of alternate the sign. So you go plus, minus, plus. Yeah. And if you kind of extend this to like a 4 by 4, you go plus, minus, and you just kind of continue in that way. Yeah. Yes. Yeah. Mm-hmm. Yeah. So you end up here with basically a 3-component vector. So you have the x component. That's kind of the first parentheses term. The second component is the other parentheses term, and the third, that's the third one. And so you find the direction from that, and that gives you direction. Yeah. Mm-hmm. Okay. All right. So that's cross product. Okay. So I think everyone's seen dot product and cross product before, but I think this last one probably you guys haven't seen before. Okay. And so this is called a dyadic product, or in other words, called the outer product. And this is one that I really wish that someone had taught me when I was in college, because if you guys decide to go to grad school and you take kind of a higher level like differential based class, like you take a high level structural mechanics class, high level fluid mechanics, they kind of already assume that you know what this is, but no one actually really teaches it to you until you kind of teach it yourself, right? And so hopefully maybe this is probably the first time you guys are seeing this, but it's a cool one. And so I like to think of this as kind of the opposite of the dot product, okay? Right, and so what this does is it takes 2 vectors, and so you multiply them. Okay, and so you're going to multiply 2 vectors in a way it's such that you don't get a scalar, you don't get a vector, right? And so you're going to multiply 2 vectors in a way that you actually get a matrix out of it. Okay? Okay. Okay. And so the way that I like to think of this is that you're making kind of a matrix, and the components of that matrix are going to be basically every combination of the components of your vectors. Okay. And so let me show you the case for a 3 by 3. I think it'll be a lot more clear. And so the way that you denote an outer product is you do this X with kind of a circle around it, right? And so if you ever worked with the equation editor in MS Word and you're kind of wondering what that symbol was, that's what the symbol does. It's for an outer product. Okay. And so the result of this is going to be a 3 by. Let's assume that A and B have 3 components. Okay. So they have AX, AY, AZ. Okay. Okay. And the result of that is going to be a 3 by 3 matrix. Okay. Okay, so the way I like to do this is I like to put the components of A kind of on the rows like this. Okay. Okay. And then I put the components of Z on the columns. Okay. And then what you're going to do is you're just going to make them. Okay. And so this upper left entry here is just going to be the product of AX and BX. Okay. This second entry on the first row is going to be AX BY. And then the third entry in this column is going to be AXBZ. Okay. And so, I'm just kind of, everything in the first row is going to have an AX. Everything in the first column is going to have BX, and so on and so forth, right? And so you can almost think of this as, we're expanding, all the different kinds of component combinations that are possible and putting it in a matrix. So let me go ahead and fill in the rest. Okay. So this can be AY BX. This is AY by. This is AYBZ, AZBX, AZBY, AZBZ. Okay. Okay. And so that's how you form the outer product or the dyadic product between two vectors. Okay. We won't use this too much in this class, but it's really useful to know because I know some of you here are graduate students, and so you might see this in another class. And I guarantee you in that other class, they're just going to assume that you know this. And so, it's good to know. Okay. Okay, so any questions on this before we segue into matrices? Okay, question?
What would be like an example?
Yeah. So an example that I know from fluid mechanics is that you can take the outer product in between two between the velocity vectors, and so you have a velocity vector in one way and a velocity vector another way, and then that gives you an expression of the turbulence stress. And so once you start to learn like kind of high level like turbulence in fluid mechanics, they'll teach you a term called the Reynolds stress. And so the way that you compute the Reynolds stress is from this. Yeah. Okay. All right. So let's talk about matrices. All right. And so matrices, you guys have all seen matrices, but kind of the formal definition for a matrix that I like to use is it's a structured array of numbers arranged in a 2D construct. Okay. Right. And so an example of a matrix is just you see right above there. Okay. And so it's a 2D kind of shape of numbers. And so the entries in the matrix, which are each individual entry here, a lot of times they're called entries, but sometimes they're called elements. Okay. Okay. And oftentimes, a matrix will be characterized by the number of rows, the number of columns that it has. Okay. And so probably the most common matrix you'll see, especially in applied applied engineering, is square matrices. And so square matrices will have the same number of rows and columns, but it's also possible to have an uneven number of rows and columns. And so a lot of times when you talk about a matrix, the first thing you kind of talk about is how what the size of that matrix is, or how many rows and columns that it has. All right, any questions on this so far? Okay. All right, so let's talk about some special matrices. There's only two. Okay. And so the first special matrix that we'll go over is the zero matrix. And so zero matrix is simply a matrix where all of the entries are zero. Okay. And so kind of boring. And so the the way that we usually denote it, okay, And so usually, you know, my notation for matrices is I like to put a little underline under the symbol. And so if I put, you know, if I put a 0 underline here, that underline means that it's a matrix of some kind. And so let's say that this is a 3 by 3 0 matrix. And so all it's going to be is, you know, all the entries are just 0. Okay. Right, so that's the 0 matrix. Next, let's talk about the identity matrix. Okay. And so the identity matrix, it's always going to be a square matrix. Okay. And so the identity matrix is square. Okay. And so a square matrix, all it means is it has the same number of rows and columns. Okay. And so for an identity matrix, all the entries are going to be 0, except the diagonal, which are going to have a value of 1. Okay. And so usually we denote the identity matrix with an I. Okay. And I'm going to do an I underline here to denote that it's identity. Okay. Okay. And so if we have a 3 by 3 identity matrix, it looks something like this. Okay. And so you can see that we have a 1 on the main diagonal. And so that's going to be a 1 in the top left, in the middle, and in the bottom right. And everything else is 0. Okay. And so probably what you guys already know is that if you take an identity matrix and you multiply it by another matrix, you get that other matrix back. Okay. And so that's why it's called identity, because it, you know, it always gives you identity no matter what you multiply it against. Okay. And so if you take some matrix A and you multiply it by I, okay, you end up with A back. Okay. Right. So the only requirement is that A has to be the same size as I. Otherwise, you can't perform the matrix multiplication. Okay. Okay. So any questions on 0 matrix or identity matrix? Okay. All right. So now let's talk matrix operations. Okay. All right, so first let's talk about transpose. Okay. Okay. And so matrix transpose, all you're doing when you transpose a matrix is that you're exchanging the rows and the columns. Okay. All right, and so if you have a matrix A, it looks like this. Okay, so let's say that we have a 3 by 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. If you wanted to take the transpose of this, the way that I usually do transpose, I take the rows and I just write them in as columns. Okay. And so let's take this first row right here. Okay. And all we're going to do is write this in as the first column here instead. Okay. Okay. And so instead of 1, 2, 3 going from left to right, you're going to have 1, 2, 3 going from top to bottom. Okay. And then same thing for everything else. Okay. And so instead of the second row being 4, 5, 6, our second column is going to be 4, 5, 6. Okay. And instead of our last row being 7, 8, 9, then our last column is going to be 7, 8, 9. Right. Okay. So all you're doing is just taking the rows and just kind of, doing a 90-degree turn and just kind of writing them down as the columns. Okay. So that's usually the fastest way that I find to take the transpose. Okay. Okay, so that's transpose. And so the next operation that we'll go over is matrix addition. Okay. And so, just like you can add two vectors together, you can add two matrices. Okay. And the logic behind it is exactly the same. Right? And so remember, when we added two vectors together, we just added together their matching components. Okay. And so when we add two matrices together, we're just going to add together their matching entries, the matching elements. Okay. And so you basically just take, what are the entries in one matrix and the other one, you just add them together. Okay. And so the only, the requirement here is that both of the matrices that you're adding together, they have to have the same size. Okay. So they have to have the same number of rows, same number of columns. Yeah. Okay. And so if you have, two matrices here, and so we'll call this A matrix A. So we have A12, A11, A12, A13, A21, A22, A23. Okay. Okay. And then we add that together with another matrix B. Okay, so we'll see this is B11, B12, B13. This is B21, B22, B23. Okay. Right. And so our resulting matrix C here is going to have the same size as A and B. Okay. And then the entries of C are just going to be, you're just adding the entries in the same location. Right. And so I'm not going to write everything here, but let's say let's take the top left entry. Okay, so the top left entry is going to be A11 plus B11. Okay. Okay, so the second entry in the first column is going to be A21 plus B21. Okay. And the last one is going to be A31 plus B31, and then so on and so forth for the rest. Okay, so I think you guys can kind of fill in the rest. Okay, so any questions on this so far? Okay. All right, so now let's go over a matrix multiplication. Okay. Right, and so there's two kinds of matrix multiplication here. Okay, so the first one is you can just multiply a matrix by scalar. Okay. Okay. And when you multiply a matrix by scalar, all you have to do is just kind of the same thing we did for the vectors. And so you just multiply every single entry by that same vector, or by the same scalar. So if we have a scalar S and we multiply by matrix A, and so the result of this will be SA11, SA21, SA31, SA12, SA13, SA22, SA23, 32, sorry. This is SA23 and SA33. Okay. All right. And so that's multiplication by a scalar, so pretty straightforward. Okay. But you can also multiply two matrices by each other. Okay. And you can also multiply a vector in a matrix together. Okay. And so when you do this, there's very strict requirements on the size. Okay? And so when you multiply two matrices together, the number of columns in the first matrix has to match the number of rows in the second matrix. Okay. And the reason for that is, it's just so that we can perform the appropriate arithmetic. And so the way that you denote matrix multiplication is you simply, put them next to each other. Okay. No social distancing, just, A and B right together. Right. And so if we wanted to perform this, I'm not going to do everything because it's a lot of arithmetic, but I'll at least show you, kind of at least my thought process that I go through whenever I do this. Okay. Okay. And so you can see, if we write out the sizes for this matrix. Okay. So in this case, we have a 3x3 matrix for A. And we also have a 3x3 matrix for B. Okay. And so one easy way that I like to do to just to check if the sizes are compatible is that if you write out the two sizes of the matrices next to each other, and you compare these two inner numbers here, okay. And so for the matrix A, that second 3, that tells you how many columns are in matrix A. Okay? And the first 3 in the second one tells you how many rows are in matrix B, right? If those two numbers match, then you're good to go. And then you can multiply the matrices. Okay? The resulting matrix, okay, will have size that's equal to kind of the two end parts. Okay. And so in this case, it's kind of, I wish I picked a better example, but in this case, the result is going to be a 3, which is this guy, okay, 3 by 3 matrix. Okay. And so that's how I usually check the sizes for matrices when you're multiplying. Okay. And then to actually perform the multiplication, the way I like to do it is I do it by rows and columns, right? And so we take this row of the first matrix and this column of the second matrix, okay? What I usually do is I look for the place where they intersect, okay? And so in this case, they intersect in the top left corner, okay? And so if you draw out kind of your resulting matrix here, okay? If you take this row and this column, what it's going to do is going to give you the entry that's in the top left of your resulting matrix, okay? And the way that you compute that is if you think of this as a vector right here, okay? You have a vector A11, A2, A12, A13, okay? And you think of this column right here as another vector, okay? What you can do is you can take the dot product in between those two vectors, okay? So we learned scalar product earlier. And then the result of that scalar product is going to go into this entry right here. Okay. And then you can repeat that same logic for every other entry of the resulting matrix. Okay. And so you just take rows in the first column and rows in the first matrix and columns in the second matrix. And if you just kind of find where they intersect and then take the dot product in between the two, that'll give you the entries in the resulting matrix. Okay. So I'm not going to write that one out because it's a lot of arithmetic, but that's usually kind of the logic that I follow for that. Okay. Okay. Any questions on this? Yeah. Exactly. Yeah. Exactly, yeah, yeah. So as long as the inner ones are the same, then you can perform the multiplication. Mhm. Okay. All right, so I'll save eigenvectors and eigenvalues for next time, because I kind of want to spend a decent amount of time on that. But I do want to just quickly review determinants before we go for today. And so a determinant, you know, every square matrix has a determinant, okay? And so the determinant is basically a scalar number. Okay? A scalar number that you can compute for any matrix, any square matrix. Okay. Right. And what this scalar number is, it's kind of it's an important metric for, you know, actually a lot of different things for the matrix. Okay. But probably the one that probably you guys are most familiar with is you can check whether the matrix is singular or not. And a singular matrix, all that basically means that you can't invert it, okay? Or if you try to form a linear system of equations with a singular matrix, it's going to have no solution. Or it has a solution, but it's just all zeros, which is not interesting, okay? And so the way that you determine if a matrix is singular is if the determinant is 0. Right. And so I think, you know, we'll start from this from next time, because it's just about out of time. But, you know, we already kind of saw determinants when we went over cross products. But, you know, I'll review it one more time at the beginning of Wednesday. Okay. All right. So thank you guys for coming today. For everyone that's in person, everyone on Zoom. You know, we'll see how this goes. And so, you know, if you guys on Zoom want to give me some feedback on how this went, you know, I think that would be really helpful. But thank you guys for coming. Thank you guys for tuning in. Have a great rest of your day, and I'll see you guys on Wednesday.
Question.
Yeah.
Is it okay if I just finish work at 4?
Yeah.
So today I only work 6 hours.
Absolutely, yeah. So I mean, that's kind of why I have this, because I know people's schedules are a little bit up in the air and people don't feel comfortable. So yeah, absolutely. You can stay like that. Yeah. So the only thing is, you know, when we do the exams, you know, I would ask you to come in person for those, but for all the lectures, you can do.
Perfect. Thank you so much.
Yeah.
Appreciate it.
Yep.
I'm in your next class.
Yep.
The one across.
Yeah, the CS is the one. So if you go across the courtyard, it's going to be. I think it's CS3.
That one you see like first time across the parking structure, right?
Yes. Yeah.
All right, thank you.
Yep. See you there. All right. Bye, everybody.